High-performance liquid chromatography, or HPLC, help determine the chemical composition of unknown mixed samples, such as those containing proteins that can't be easily vaporized into a gas. A sample is first passed through the pressurized column containing a solvent that separates the sample individual chemical components, unlike gas chromatography, where the sample is vaporized before being passed through a column. In HPLC, the sample stays in the liquid form as the different compounds emerge from the column. Their transit times and relative concentration are recorded by a detector. The print result, or chromatograph, shows each compound as a peak representing quantity and exit time. By comparing these peaks to the pattern shown by known substances, and analysis can often determine the chemical composition of the original samples. Now, for the introduction, let me explain more detail about high-performance liquid chromatography, which is HPLC. High-performance liquid chromatography is a powerful analytic technique for separating, identifying, and qualifying individual components within complex mixture. HPLC utilizes the principle of liquid chromatography, where a liquid mobile phase transports a sample compound through a column packed with a stationary phase. Interaction between the analytic and column of stationary phase lead to their separating based on physicochemical properties such as polarity, molecular size, or charge. Let's move to the objective of this experiment. First, to determine the rotation time of a standard solution, which is caffeine. Second, to identify the caffeine peak in a soft drink sample. Third, to identify the amount of caffeine in the soft drink sample using a response factor method.
Next is methodology, where I will explain for the component and its function. First, we have solvent receiver. It holds the mobile phase, or so-called solvent, that will carry the sample through the system pump. Next, we go to the pump. It delivers the mobile phase at a constant flow rate, ensuring consistent pressure and flow throughout the system. The third step is injector. Injector introduces the sample into the mobile phase stream. It can be manual or automatic. Next, we have column. Column contains the stationary phase, where the separation of compounds occurs based on their interaction with the stationary phase. Next, we have detector. Detector is a monitor that separated components as they elute from the column and generate a signal proportional to their concentration. Common types include UVBs, fluorescence, and mass spectrometry detector. Next is chromatogram. Chromatogram collects and processes the signals from the detector, converting them into a readable data and graphical outputs. Next is the last one. The last one is a waste container. It collects the mobile phase and any elite components that are not analyzed or collected.
For result, rotation time for caffeine standard is 2.482 and the area of caffeine is 6,249.48779. For caffeine in Coke, we got rotation time is 2.481 and peak error is 7,001.12305. And the last one, for caffeine in Levita, the rotation time is 2.479 and the peak error is 1.11511 times to 10 power of 4. The table was constructed from the result. To find the response factor RF, the peak area of caffeine standard must be divided with concentration of caffeine standard, and we will get 6249 mg per ml. Next, to find concentration of caffeine in sample, we use formula peak area of caffeine in sample divided with RF that we calculate just now. So, for the concentration of caffeine in the coke, we got 1.12035 mg per ml. But we need to get answer in ppm, so the answer in mg per ml must be changed into ppm. 1 mg per ml equal to 1000 ppm. So for the concentration of caffeine in the coke, we got 1.203 times to 10 power of 3 ppm, and for the concentration of caffeine in the Levita, we got 1.784 times to 10 power of 3 ppm.
Moving on to our discussion. The liquid chromatography result shows that the Levita has a higher caffeine concentration compared to Coke, indicating that Levita contains more caffeine per unit volume. This aligns with the expected formulation differences, as energy drinks like Levita are designed to provide a stronger stimulant effect than soft drinks like Coke. Next, the minimal difference in retention times confirm that the detected peaks corresponds to caffeine with little interference from other compounds. The slight variation in peak areas could be due to the differences in sample composition, dilution factors, or instrumental conditions. Lastly, to improve accuracy, a caffeine standard could be analyzed for calibration, and additional techniques like mass spectrometry or UV absorbance could be used for precise quantification.
So, in conclusion, all objectives have been successfully achieved. We determined that the retention time for a standard solution of caffeine is 2.482 minutes. Other than that, we were able to identify the caffeine peak of our soft drink samples, which is Coke has a peak value of 7001.12305, while Levita have a peak value of 1.11511 multiples 10 power of 4. Then we found that the amount of caffeine in Coke is 1120.3 ppm, whereas in Levita it is 1084.3 ppm.